Let's look at a few implications of the definition of potential difference with respect to electric field. I'm writing it out this way. Okay. This is the full-blown mathematical form. Okay. So what happens if the electric field is perpendicular to the path we follow? Well, what does it mean about the potential difference along that path? If E is perpendicular to delta S, knowing that E dot ds means finding the component of E in the direction of S, it means that's zero. Okay. So if I've got an electric field that points this way, okay, so this is my electric field, and I go this way in space, this would be my delta S. If those are perpendicular, then the potential difference between here and here is zero, because this integral would give me zero. So this tells me something, that electric fields always point perpendicular to lines of constant potential. So if I have a series of lines, now these are not physical objects. These are not physical objects, but if I have a series of lines here, and these are lines of constant potential, meaning if the potential is 3 volts here, it's 3 volts here, and it's 3 volts here. Okay, but these different lines would have different voltages. So I'll just say this is, let's just make it easy. This is 0 volts and 10 volts and 20 volts. Okay, just to make it simple. Well, this principle that we just saw means that the electric field, I can draw lines of electric field because they're always perpendicular to lines of constant potential. And so the electric fields would kind of perpendicular, and a sharp curve there. That would be my electric field. Here's perpendicular, and then perpendicular, and that would go off because that's curving too much. Okay. Those would be my lines of electric field. But the point is that every line of constant potential is perpendicular. Okay. Now, another thing that we know, and I need to be careful, I actually drew my vector directions in the wrong direction here, so I need to clarify that. So they're all perpendicular, but this minus sign means that if the potential difference is big, or positive, that means the electric field is in the opposite direction as the path I'm taking. So that means these are actually this way, because I'm growing in potential difference. I gotta cross out those arrows. I'm growing in potential difference this way, which means the electric field must be pointing opposite. That's what this minus sign means. Okay. So we know that electric fields point perpendicular to lines of constant potential. We call those equipotential lines or equipotential lines. And we know it points towards lower potential, which is something we actually knew before, but now we can see from the rigorous mathematics. Okay. All right, so that's two things we draw from it: perpendicularity and pointing towards lower potential. Now, another thing that's really powerful is what happens when the potential is zero for some reason. Okay, potential is zero in an area. Well, that means either the electric field is perpendicular to the path I'm following in that, or the electric field is zero. Okay, so let's look at some hunk of metal here. Here's a peanut-shaped hunk of metal. It's a conductor. That's what's important. It's a conductor. Okay. Now let's suppose that I have an electric field in there. So I get some electric field in this conductor. Well, the conductor has the mobile electrons, the electron C, and they will move because they'll feel this electric field and therefore a Coulomb force. And they'll move in different directions, okay? They'll fly opposite this electric field. And they will keep doing that until they create an electric field. So a bunch of electrons might pile up here, leaving bare nuclei over here. And these create an electric field that grows until it cancels that out. So this would be E applied, and this would be E induced. And so the applied field causes the electrons to fly away, which then the separation of those charges causes an electric field to grow until it equals that and cancels that out. Okay, now that's review. That's review. But what it means is inside a conductor, E is 0. Okay, and we'll be specific here for this case. A conductor in electrostatic equilibrium. Okay, that means no currents flowing, because we can actually create current to flow by sucking these electrons off and putting them back over here with like a battery or just a circuit of some sort. We'll see that in later discussions. Okay, but if we just assume a block of metal sitting here, then those electrons pile up until the electric field is 0. Okay, so if the electric field is 0 inside this conductor, then what is the potential difference between any 2 points on that conductor? The answer is 0. Because if E is 0 inside this, no matter what path I take, I can go from here to here, here to here, here to here, here all the way around to here. It doesn't matter what path I take. If the electric field is 0 everywhere along that path, then the potential difference is 0. So what happens is a conductor in electrostatic equilibrium, because its electric field is 0 everywhere inside it, we have it being a constant potential. Okay, is that a constant potential? So if the potential over here is 3, then the potential over here is 3, and everywhere else. So that's another thing we can draw from this. So a conductor in electrostatic equilibrium is a constant potential, or an equipotential surface everywhere there. Some other details that we won't focus on too much now, but we can find, and the text goes into, that the electric field at the surface is non-zero, but it has to point perpendicular to it for the same reason as we saw here. If the surface here is at a constant potential, then the electric field must point away. Okay. All right, so that is 3 things we can pull away from: the perpendicularity, pointing towards lower potential, and constant potential because of 0 electric field in a conductor in electrostatic equilibrium.